Okay, we're going to solve problem 7 here. And the problem we're given is we're told a ball is thrown horizontally with a velocity equal to 26 meters per second, travels a certain distance, and then it hits the ground. So it's kind of going something like this, and then it's hitting the ground over here. We know this distance is 56 meters. What else do we know? We're asked to find the height. This is what we want to find. Okay, with the initial given data, this is what we're given, but there's some other pieces of information we know right off the bat, right? We know acceleration. I need to change pencils here. Okay, we know acceleration. We know acceleration in the vertical direction equals what? Minus 9.8 meters per second. In other words, 9.8 meters per second pointed down. We know acceleration in the x direction is 0 because we're told it was thrown with a certain velocity and then there's no more accelerating forces applied on this while the ball falls, so we know that. What else do we know? Obviously we know the starting and the ending distance. We know the starting velocity. We don't know the ending velocity. Okay, a couple of key things that you really need to recognize about these projectile problems that make it very easy. They talk about it back here in the book. Let me point out a few things. Okay, by definition, a projectile is an object that moves in 2 dimensions under the influence of gravity and nothing else. Okay, so an airplane with the jets still blowing would not be considered a projectile, but something that I throw off the top of a building would. I give it an initial velocity, or I could drop it, either one, it would still be a projectile, but once I release it, there's no forces acting on it besides gravity. And as they point out here, for most of the, somewhere in here they talk about that, there we go. Although they are influenced by air resistance, the effective air resistance is small for reasonably dense objects moving at modest speed, so we can ignore it for the cases we consider in this chapter. Now, they're not going to ask you to calculate the projectile motion of a feather or a flat piece of paper. But most of the things they're going to ask you to consider, you can presume that air resistance is negligible and just set it aside. So these are key points here. Because the form of motion will always be the same, the strategies we develop to solve one projectile problem can be applied to others as well. In other words, at this point, once you recognize that it's a projectile problem, it doesn't matter if it's a ball, a bullet, a cannonball, a bird falling, it doesn't matter what it is. Whether it's thrown with an initial velocity or not, they're projectile problems. Now, here is the real key point here. And you should have seen this as you were working through the chart, but this is what makes everything so much easier. The horizontal and vertical components of an object undergoing projectile motion are independent of each other. They talked about it a little bit back here in, let me get that light. They talked about it a little bit in this chart right here. They showed there were 2 balls launched at the same time. The yellow ball was launched with a horizontal velocity, but no vertical velocity. The red ball was just dropped. And the thing about it is, you notice they both hit the ground at the same time, and if you track them across this way, you'll see that at the same point in time, they are at the same elevation. In other words, the vertical behavior of each of these balls was completely independent of any horizontal velocity given up here. What does that tell me? That tells me that I can take any kind of projectile problem and break it into 2 parts. And they describe those 2 parts here on the next page. So if we go to page 81, they tell you right here. Projectile motion is made up of two independent motions. Uniform motion at constant velocity in the horizontal direction and free fall motion in the vertical direction. That makes it really nice. You learned in chapter 1 how to deal with, well, in chapter 2, how to deal with uniform motion at constant velocity. So that's easy. And then you also learned about how to solve free fall. So a problem like this, while it looks complex, is really just two problems in one. You separate the two of them out and solve them independent of each other. It makes it so easy. Now let's go through and demonstrate by doing problem number 7 with our ball. Okay? So again, I can look at this as two independent problems. What's happening in the y and what's happening in the x. So this is my y and this is my x. Let's look first at what is going on in the x direction. Okay? So not looking at any of the change in height, let's only look at its behavior in the x direction. The ball starts with an initial velocity of 26 meters per second. And then at some point over here, what's its velocity going to be? Its velocity has no acceleration. I know you want to say, but it hit the ground, it stops. Well, yeah, technically, but at the instant it hits the ground, or the microsecond before it stops when it hits the ground, it does have a velocity. In the absence of anything, any acceleration force, this velocity will remain unchanged. We'll learn a little bit about Newton's laws, but one of Newton's laws is an object in motion will remain in motion unless acted upon by an outside force. There are no outside forces acting on this, so it's going to have the same velocity from beginning to end. Its horizontal velocity is unchanged. That's what you call uniform velocity. It's moving in a straight direction, or a straight line with a constant velocity. That is the definition of uniform motion. Okay? Now I'm actually asked to find the height that this ball will fall, and honestly the height doesn't come into play here in the x direction at all, so I'm not even going to look at the x direction. Now let's look at what's going on in the y direction. Okay, so in the y direction I have the ball that starts here. Now, does it have any kind of an initial velocity in the y direction at all? No, it doesn't. We're told that it's thrown with a horizontal. It said the ball thrown horizontally, so it has no vertical component of velocity at all. So it starts off with a velocity equal to 0, velocity y equal to 0. So what does the ball do again? Look only in terms of its change in vertical position. It goes from whatever height this is up here at h down to the ground. So it falls some distance h. Do we know how long it takes? No. Do we know anything else? Absolutely. It's a free fall problem, so we know that acceleration is minus 9.8 meters per second squared. So again, I have two problems. I have uniform motion and I have a basic free fall. Now ultimately I'm looking for h, right? That's what I'm trying to find. So I don't even really need to look at any further here. It's of no use to me. This is the one I want to focus in on because this is the variable I'm trying to find. So do I know an equation that relates acceleration, height, and velocity? Or can I determine, for example, maybe I could do this in 2 steps. Can I determine the ending velocity? Sure, I could probably do that pretty easily. Let's draw what the curve of this looks like, by the way. This velocity is going to start at 0, and this is velocity versus time. It's going to start at 0, and because it's going down, it's getting more negative. Okay, so the velocity is going this way. It has a slope of 9.8 meters per second squared. Let's come back and look at our equations we had back here from chapter 2. So again, for motion with constant acceleration, which is what I have, they're free fall, what do I know? Well, I have this equation that relates velocity and time, so I could solve for the final velocity. I have this equation which takes distance, velocity, acceleration, and time. Could I use this one? Well, I don't actually know the time. I know the acceleration, and I don't know the distance. I'm looking for that. What about this one? Could I use this one? Well, distance is what I'm looking for. Acceleration I know. Once again, velocities I don't know. So I might have to do this in a couple of steps. Uh-oh, hold on one second. I have an interruption. I'll be right back.